My name is Sjoerd, and I was going to present this with my colleague Ricardo, but who actually did most of this work, or a lot of the work, but he couldn't make it, so I'm just presenting today. This talk is about LLVM-MCA correlation for AArch64, and well, first of all, I'm going to explain what it is, and then maybe more importantly, why that is an interesting thing to do. Maybe an alternative title of this talk could have been Performance Analysis Journey, our Performance Analysis Journey for a new CPU. And I want to start at the kind of the very beginning, how this all started for us. It started with a regression in a workload for us. It was a tiny code change that resulted in a lot in worse performance, runtime performance results, about 10%. It was a fairly large application, and almost literally this change caused a 10% overall regression. So after the code change, we emitted some vector code, and on the right, the fast scalar code was the original code that was a lot faster than the vector code. This is kind of unusual. It can happen, but this is typically not what you see. But for this particular case, we don't need to understand the high-level semantics of the instructions or anything like that. Just some high-level observations are good enough. So what you see is the vector code is, in terms of number of instructions, is kind of about the same, slightly less actually. The vector instructions, they work on 2 data elements, which isn't much, but yeah, it is what it is. So just looking at this, you would expect maybe the same performance, maybe slightly worse, but you definitely would not expect a 10% overall regression. That's strange. Just looking at this, you can't tell actually much more about this. You can maybe look at some latencies, you can maybe look at dependencies, but then still, yeah, what can you say? So the problem that we have here is that we don't know how to vector it. We don't know why we shouldn't vectorize this, or we don't know how we should vectorize this differently. So yeah, what we are actually missing here is a tool for compiler engineers to evaluate the workloads and then to come up with a different code generation strategy. So the outline of this talk, the outline of our journey too, is kind of, there's 2 parts of the story. First, we were looking for an open source performance analysis tool for compiler engineers to evaluate workloads and then to make different decisions, possibly. Then, once we have that, we want to investigate the quality of this tool. So we want a performance analysis tool that makes static predictions of the performance. And then what we want to do is we want to check how good these predictions are with results obtained from hardware. We are doing this for our new NVIDIA Grace CPU. That's a high performance CPU meant for data centers and HPC. And it's based on ARM IP. It has up to 144 cores, Neoverse V2 cores. And yeah, I just want to highlight that our findings are not actually specific to Grace. They are kind of generic AArch64 observations. Zooming in a little bit into our approach and contributions, the first step is actually to enable LLVM-MCA for Grace. That's going to be our static performance analysis tool. And then in terms of correlation, we have kind of 3 steps, sub-steps. We first extract hot codes from certain workloads. We want to do this automatically. Then in the second step, we take these hot code parts, we run LLVM-MCA, we get these static performance predictions, and then we compare them with hardware results, runs obtained from hardware. And then we are going to look for divergences where the trends are not the same, and see if we can fix up tools or other parts of the let's say the flow. So to put this flow, this performance analysis flow into perspective, for the example, our motivating example, one approach could be to kind of write a micro benchmark, but there's a lot of problems with this. It's first of all, it's time consuming. Writing a micro benchmark is actually very difficult. Tiny differences can make a big difference, and you can easily get to the wrong conclusions. And then finally, when you write when you run your micro benchmarks, it actually may not give you the insights that you need. For example, if you run your micro benchmark with linuxperf, you can find more backend stalls, but that doesn't give you enough information. Another approach is cycle-accurate simulation. It's most accurate. It gives you all the details you need, but so there's no substitute for that. But there's a couple of disadvantages. It's slow, it's more difficult to use, and it may not always be available. So we want a tool with a different trade-off. We want something that is faster than cycle-accurate simulation, but still capturing the performance trend very well. So the flow is we start with our workload, our app, we run Linux perf, we get the hotspots, which can be a function, a loop, or a basic block. And then we take that hot code and we want to run this through our performance analysis tool. And what we want is metrics like the pipeline behavior, the instructions per cycle, and the resource utilization. So what we're looking for is a tool that fits into this circle with the question mark. Now, what we want from this tool is something like this. We want a timeline view of instructions. So this is the same example as shown before, but now annotated on the kind of the left-hand side, the kind of the pipeline behavior, the timeline. So you'll see letters like the capital D, which stands for dispatch, the E for execute, and the R for retiring. Now, this actually gives you already the insight why this particular motivating example, the new vector code is slower. Just by looking at it, you see that the timelines are a bit more stretched, and this is caused by dependencies, an increased length of the critical path, and longer latency instructions. So this is this tool, this kind of information gives us the insights that we need so that we can actually now understand why this vector code is not what we want and how to do things differently. And as I mentioned, the tool that we're going to use for this is LLVM-MCA. MCA stands for the Machine Code Analyzer. It's part of the LLVM project. It's in the mono repo, and it uses all sorts of components there. Most importantly, it relies on shelling models. And a shelling model is a description of instructions. It describes the latencies. It describes the resource utilization. Shelling model also describes the resources of the CPU, like the resources and the number of resources. There's two kind of, in LLVM, in the LLVM project, there's kind of two use cases for the shelling model. First of all, it's used by the compiler for code generation, instruction shelling. Secondly, it is also used by LLVM-MCA for the performance analysis. And that's going to be our use case. So LLVM-MCA, you can give it a sequence of assembly instructions, and then it provides instruction information such as the latency and throughput, as I kind of showed you in the previous slide. It can give a lot more insights too. So what we did is enable LLVM-MCA for our new Grace CPU. And what that meant is we had to write a shelling model. So that's what we did. We wrote a new verse v2 a new verse v2 shelling model. Before it was using the new verse n2 model. So with the shelling model, we now had the tool available. But since shelling models are also used for code generation, we verified that we did not accidentally regress performance of a number of workloads. So when that all looked good, we actually started using LLVM-MCA. We used it in performance analysis for some of the problems that we had. And this tool immediately allowed us to see problems, improve vectorization for a number of cases, because we noticed that, for example, latencies, instruction descriptions were just wrong. So we had all sorts of patches related to cost modeling. Now, with LLVM-MCA available for Grace, we wanted to take the next step, which is maybe the more interesting step. We want to do correlation. So what we want to know is whether these static performance predictions by MCA are accurate. Can we trust these predictions? So what we want from this is that kind of the trend is exactly the same as the hardware results. And I'm going to show you later how we do this. But we kind of already knew that LLVM-MCA has quite a number of limitations. By design, it doesn't predict the front-end throughput of the CPU. For example, it doesn't predict the fetches, instruction fetches. It doesn't model control flow. There's all sorts of assumptions made by the tool, how this processor looks like. The quality of the sailing models that it is using affects the performance analysis. So there's quite some restrictions and limitations. The question is, does this matter for our performance work? That's what we want to investigate. So what we want is some criteria for these predictions, and that's going to be our correlation methodology. Now, kind of very generally, what you want from a correlation methodology, that if you have a set of interesting workloads, you want that, for example, that the predicted performance is, let's say, within 5% of the hardware result. So, for example, if your workload finishes in 100 cycles or 100 seconds, you want that the predicted performance is, let's say, within 95 cycles or 105 cycles. So if you take the ratio of your predicted app and you divide this by your runtime app, you want to be within the range of 0.95 or 1.05. You want to do this for a relatively large number of apps, so you kind of capture a lot of different cases, and that should give you confidence in your predictions. And preferably you do this in an automated way. The problem is that LLVM-MCA does not calculate, let's say, the predicted runtime of an app, as I kind of showed you. It basically consumes straight line assembly code and that's it. So we need to do something else. And so our approach is going to be different. Our approach is that we compare two equivalent assembly codes, and equivalent is going to be important. And what we want is these two equivalent assembly codes to be generated from the same source. So what we do is we take one C++ kernel, typically an inner loop, and then we generate two assembly kernels, A and B, where A and B are equivalent. Equivalent in this case means that they kind of process the same number of data elements. Think, for example, about array elements. To give an example, when they are not equivalent is if one straight line piece of code is the result of unrolling and the other one isn't, then the unrolled version processes more data elements. So in that case, they do a different amount of work and they are not equivalent. Or if one of the variants has been loop vectorized, it also processes more data elements, and then they're also not equivalent. So we want to generate these two different variants by compiling the same source with different compiler options, and we want to do this in an automated way so that we can do a large sweep of different workloads. So the first step in this correlation methodology is going to extract kernels from, in this case, TSVC. TSVC stands for Test Suite for Vectorizing Compilers, and it's part of the LLVM Test Suite. On the top, you see actually one of these kernels, and the first step is to annotate. We do this with scripts to annotate the inner loops, and we place these markers just outside, because if you put them inside, that affects code generation, and that's not what we want. So with these annotations, we then compile it to generate comparable A and B assembly versions. And we do this by always disabling the loop vectorizer, because as I mentioned, that affects kind of the number of data elements that the kernel works on. But then we toggle the SLP vectorizer on or off. And that does not influence the number of elements. We can then guarantee that we have equivalent versions. So when we do that, on the left-hand side, when we disable both the vectorizers, we get straight line code. You see 5 floating point multiplies, and that kind of corresponds with the C code. For the B version, when we toggle the SLP vectorizer on, we see some vector code. You see one vector instruction that processes 4 elements, and there's one scalar, so that also totals to 5 floating point operations. We generate assembly code, we look for these markers, and then we take the inner loop kernels. Then we run LLVM-MCA on these 2 versions. And then what we want is that the predicted performance of A is, if the predicted performance of kernel A is faster than the predicted performance of kernel B, then what we expect is that the runtime of app A is also smaller than the runtime of app B. That's kind of our correlation expectation. And here are some results. We have more results, but this is for TSVC, as I mentioned. And they are just some interesting data points are highlighted here. The first one is the correct predictions, where assembly version A is faster than B, and we see exactly the same on hardware. And that's the number one annotation on the data points. And actually, they are within 10% of each other. So kind of okay. Number two is we see incorrect predictions. So where the hardware is where the runs on hardware shows a speed up of A over B, but on LLVM-MCA tells us exactly the opposite and a very significant difference. We also have cases where we don't have any assembly snippets, and just by a limitation of our scripting, because of the annotations of the markers, we expect them to be in a certain order, first the start and the stop. But sometimes, due to basic block reordering, they are in different orders, and then we can't pick up these. We cannot identify the inner loops. Sometimes the number four is when they are exactly the same. That doesn't mean that they are exactly correct predictions, but that means that there's no difference in cogent. So toggling the SLP vectorizer on does not result in any difference. And then number five is we have quite a lot of interesting points to analyze, but we don't have the LLVM-MCA version for that. So that's something we could investigate. So we have quite a number of cases where things diverge, and that's what we want to investigate, what we could do about this. The things we found, we identified by doing this correlation exercise fall into basically two areas. First of all is the Schelling model, and the second one is LLVM-MCA itself. So I'm going to summarize all the Schelling model fixes that we did, but just by doing this, we found a lot of issues in the Schelling model. And because Schelling models, they took some inspiration from each other, we had to fix up quite a number of Schelling models. And even very basic things like ALU instructions, descriptions that were just wrong. About LLVM-MCA, we found that instruction fusion is not modeled at all. That is kind of to be expected, but that's what we also saw. So for example, a compare and branch can be fused, and that's not modeled. It's also important for SVE. The SIMD extension has certain instructions that basically have a zero latency, and that's also not modeled. So when we encounter this, we know that MCA is not giving the right prediction. There is one fundamental problem that we found for which we have no fix. I'll try to briefly explain that. And this is not only for post-increment stores, but it's kind of a general problem, but it's most visible here. The short version is that a post-increment store is actually two operations. It's a store and then an increment. And on the left-hand side, you see a dependent store and a multiply operation. And that's the post-increment store. On the right-hand side, this is made explicit. The increment is made explicit with an additional add. The correct behavior is on the right-hand side, but LLVM-MCA gives us the left-hand side. The short version is that a store this particular store is broken down in multiple micro-ops, and this is not modeled at all. This is not a simple table gen fix like some of the things that we fixed. This is kind of an open question how to do this. We discussed this on Discord, and yeah, we had an interesting discussion there. You can follow the link probably later. So yeah, I wanted to conclude with some observations, lessons learned, and recommendation. Yeah, we found a lot of issues in the cost model. So just kind of a good recommendation actually is maybe this is an interesting exercise just to find all sorts of issues in your Schelling model. This correlation exercise turned out, it looks simple, but it's surprisingly time consuming. and not very straightforward. If you want to do this in an automated way, I try to hint at that with our scripting to pick up the markers and pick up the assembly versions. And it looks straightforward, but it's a lot of work. We generated the kind of equivalent assembly versions by toggling on and off the SLP vectorizer. Maybe there's other ways to do that. That's to be investigated. Also, we have done this exercise for LLVM-MCA, for TSVC and some other workloads. But I don't think it's enough to actually draw a conclusion that LLVM-MCA is well correlated for AArch64, or it's not well correlated. I think we need to do more work. But the final conclusion is that LLVM-MCA is an excellent tool. Thank you very much for people working on this. It is going to be part of our toolbox. Through this exercise, we got a lot of experience. So actually, we know it's not always correct. But this exercise gave us a lot of experience. We now know what to look for. So that is useful in itself. And yeah, that's where I would like to leave it. Thank you.
So we'll have a few minutes for questions. Please come up to the microphones to ask them.
Thank you for your work and a great talk. I have two questions. So one question is, I wonder, what could be the issues that are due to the fact that the scheduling model is used for, well, instruction scheduling? And by that I mean, for example, sometimes you have to introduce workarounds in the processor models. So you have to restrict the reorder buffer size of a given processor model because it turns out that the scheduling algorithm is quadratic in the reorder buffer size.
Yeah.
Do you think this is a fundamental problem, or is there some way to, say, decouple the representation of the processing model used for MCA versus that for used in the scheduling, so you don't have to contaminate the prediction results by the workarounds you have introduced for instruction scheduling, for example?
Yes, excellent question. That's an open question that we have. Should we actually use shelling models at all for this? This is a big core where shelling is not so important. So the changes that we made in the shelling model had no effect at the runtime of the code generation or the performance that we observed. But you could think about examples where the two are conflicting. So then in that case, you will run into problems. We have not really seen this, but it's kind of easy to imagine you could end up at this. In the discourse thread, MDL was suggested. MDL stands for, I forgot now.
Machine description language?
Yes,
perhaps?
and I think that is very promising. I think it gives us more flexibility, and if we write MDL descriptions, you also possibly avoid this kind of conflict that you change something for your modeling and you affect code generation. Hopefully that answers your question.
Right. And one follow-up for the well-correlated part. So given your experience in studying how closely well-correlated the MCA predictions are with the actual performance, how close do you think we are to being able to use MCA for continuous performance tracking of a compiler? So say there is some really focused kernel or even individual basic block like in the TSVC example, and you are really interested as a compiler engineer to not regress this over time. Could you see a path to being able to use LLVM-MCA for some kind of regression tracking, but for performance? Would you be confident in the correlation at this point to run this commit per commit to see if nothing has regressed the performance of some particular kernel?
Yeah, I think that's interesting. I think for small snippets, I think if something changes, then I think it's worth investigating that. If it's always accurate, I don't know, if you see what I mean. That's what we try to investigate. But yeah, that's an interesting idea. Yeah.
Right, fair enough. Thank you very much.
Yeah.
Hi, first of all, great talks. And I have questions on the limitation of MCA. Did you run into any problems of the inaccuracy model of like memory instructions? And the other one I can think of, do you run into any problem because MCA doesn't model SMT at all?
Yes, yeah, good question. We have not seen this simply because we're not looking for this. So what I'm trying to say is we really try to focus on just the data processing instructions, the inner kernels that we're doing, for for example, vector instructions or scalar instructions.
So it just happened that the kernel you're looking at doesn't either switch the hardware threads or have significant, let's say, LMS-ish.
Yes, no, we have not looked at it. Also, I think in our case, yeah, everything is very much compute bound. So memory is not really an issue about other programming models, SMT. No, we have not looked at it. Yeah.
Thank you.
Yeah.
All right, that's all the questions we have time for right now. Please come up and find the speaker if you have more.